When I was an undergraduate student, I had the opportunity to work with an astronomer. Her work was to measure positions of asteroids. Asteroids are moving very fast on the sky, and sometimes you see them just one night. She measured the position of this particular asteroid that wouldn't be returning for years, and then she learned that she ended up being the only astronomer observing that asteroid at that time. Everywhere else in the world, all the other observatories that could have observed it, they had cloudy weather. At that moment, I knew I want to become an astronomer. I knew I wanted to become a scientist because it meant that your work builds on a larger body of knowledge, and it can be quite unique. So that's how I became an astronomer, and my expertise became exploding stars. We have many stars out there in the sky. Some of them are smaller than our sun, some of them are like our sun, and some of them are much bigger than our sun. Those ones that are more than 10 sizes of our sun, they explode as what we call supernova remnants. So they create spectacular images because there's a lot of energy that is released in these explosions. And it's a bit of a detective story for astronomers to actually figure out what happened. Because no matter how much we can estimate what kind of star it is, we don't know how old it is. We don't know, is it going to explode tomorrow or is it going to explode in a million years? So by observing these remnants of explosion that we call supernova remnants, we then work backwards to figure out what was the star, what was the mass of the star that created this remnant, and then we go and find that star in archival images. So detective work is part of the being scientist as well. This is very exciting, of course. This is part of the work I like. And having these spectacular images that you look all day, it's super fun. So having to look and find what is that remain of the star that exploded is the hardest part in this field, because often they can be so small and the emission can be overwhelmed with the brightest emission of a supernova remnant. So here you see with the circle where the tiny star that its remain of the exploding star is. And you can see how small. It's only about 20 kilometers in size, and the remnant that travels further on extends to a much larger area. It's much brighter. This is Cassiopeia A, one of the youngest supernova remnant in our galaxy, only about 300 years old. And even for this remnant, it was very hard to find that remain of the star. But my recent research actually brings me much closer to home. So we all live on Earth, and we think it's very special. But astronomers know that it is quite special. We are the only planet in our solar system that is habitable, which means it can support life. Mercury is too close to the sun, so we know it would have never been able to support life. But Venus and Mars are not too far off, and they should have been able to support life. But somehow Earth ended up being the only planet in our system that had life. So then we start our detective story trying to figure out why Earth is the only planet that has life. What are the properties that we have that other planets don't? So to do that, obviously, we have to compare our planet with all the other planets. So we'll look at the 8 major planets in our solar system, and we divide them into groups. One that we call terrestrial, which are rocky planets like our Earth, and other that we call gaseous, like Jupiter, Saturn, because they're mostly made of gas. So rocky planets, they reside closer to the stars. So we have 4 planets residing close to our sun, because rocky material can survive closer to the hotter regions. But light materials like hydrogen and helium can't survive so close to the star. They get evaporated or pushed away. So gaseous planets get to be formed further away. So in terms of supporting life, we know gaseous planets cannot support life. There is a small chance that they could, but we're going with the highest possibility, so we stick to terrestrial planets. So then we zoom into our 4 terrestrial planets, Mercury, Venus, Earth, and Mars, and we try to figure out what is it again that Earth has, the rest don't. So we try and look at the cross-section. Obviously, we can't really do this. We can't slice our planets, but we can measure in a different way. In an indirect way, we can measure and estimate what the interiors, exteriors are. So we know planets have cores and crust. Crust is made of lighter material like silicon, and the cores are made of heavier elements like iron. So when we estimate what is in the core of the planets, we find that Earth is the only planet that still have partially molten core. All the other planets are already cooled down and their cores are solidified. But Earth seems to be the only one that still have partially molten core. What that means is that basically our core behaves like a magnet, and it gives us magnetic field, which is what we're the only planet to have. So then we have to continue our detective story and figure out why is it that we are the only ones that have iron. So we have to think where all these elements come. Where does iron and silicon come from? So they all come from stars. Stars are the only places where heavier elements, those above helium, are created. All the stars are forming molecular clouds. Those are basically condensation of gas and dust spread out through our galaxy. And then those clouds collapse and they form stars. But depending on how much gas is collided in that region, you will either form stars like our sun, or you will form stars that are much more massive, much bigger than our sun. And like everything else, those stars live and then they die. And the way they die differ for these two types of stars. So if you have a normal type of star, which is like our sun, we say they die relatively gentle death. They just release the outer layers and the core of the star remains to shine for millions of years. But with the massive stars, they live much, much faster, only about a million years, and they explode. They're so powerful, they're so massive that the gravity, when they collapse, blows the whole outer layers of the star, and they're ejected as supernova shells. So the event of explosion is called supernova, and sometimes can be so powerful that outshines the whole galaxy in which these stars reside. But that supernova event marks the event in which the outer layers of the shell ejected and they form supernova remnants. In this process is where the elements are ejected. So elements are created in different layers of the star. They all start in a core, obviously. The star starts burning hydrogen to helium, and then helium into carbon, and then carbon into oxygen, and so on. Oxygen to silicon, and then silicon to iron. And then when the star burns things up to iron, it can't sustain this process anymore because iron is a very stable element. So with burning, with fusion of iron, we don't get as much energy release as the energy needed to burn iron. So in this moment, the thermonuclear reactions that are fusing these elements and provide push outwards, those reactions stop and gravity of the star prevail. And all the outer layers collapse onto the star, which then the core of the star collapses to become what we call a neutron star, or if it's really, really massive, it becomes a black hole. But the outer layers are spread out and they're ejected as supernova remnants. But this is the process by which these stars then release those elements heavier than helium into interstellar medium. And we know this by observing many of these supernova remnants. They roughly happen once per century in our galaxy, and we have about 300 of them that we can observe at the moment. So we observe them in many detail, and then we try and model what is happening. So this is a sort of projection of Casset, because we detected different ejecta from different elements, and we try to put them in a model and then manipulate them and recreate that model to understand how this process works. So you can see different elements. You can see iron in green and so on. So we basically understand how this process works, and we know that how elements get to be dispersed throughout interstellar medium. But then we continue our detective story. How does elements get to build planets? So when we look at star-forming regions in which we know stars are still being formed, and with stars we know there should be also planets being formed around them. We can look at here Orion Nebula, which is one of the youngest star-forming regions in our galaxies. And you can see those brighter regions of the image. This is where massive stars are heating the region around and making it very bright. And then as you see further away, you can see individual stars, but you still see a lot of gas and dust that will go on into building stars. When those massive stars explode, they will disseminate their elements throughout these regions, star-forming regions. If we try and zoom in, we will see little regions where we see protoplanetary disks. So we know that as the star is being formed, at a certain point, as star lights up, there will be debris disk around from which planets will be forming. And then as the massive stars release their elements, those elements will basically get embedded into these protoplanetary disks. So if we are able to zoom in further, we would see something like this. A protoplanetary disk is basically made of gas and dust, and that dust starts colliding and start creating little rocks. And those rocks collide to create bigger rocks, and those bigger rocks eventually collide to make planets, while the star is still shining in the center. So if we are able to zoom furthermore, we would see those rocks building bigger planets. And the collision basically releases heat, then melts those rocks, and that's how planets slowly cool off eventually and solidify. So this is what we think happened to Mars and Venus, but it didn't happen to Earth. So there has to be some source that somehow the protoplanetary material that was building Earth had to then create extra energy source to keep our core molten. And what we think that extra element is aluminium-26. It's a radioactive element that decays over about 1 million years and releases something like 4 million electrovolts of energy. So that's a lot of energy that can then use to keep our iron core still molten. So the question then becomes, why only Earth? And why is that existence of the molten core important? As I mentioned before, it's because we have the molten core behaves basically like a magnet, so it gives us magnetic field. That magnetic field protects us from solar wind. All the stars, big and small, produce solar winds. They're basically highly charged particles that are released from time to time from the surface of these suns. And our sun has moderately strong or moderately weak solar winds. But regardless of their strength, they have power to dissociate water. When they come to dissociate the water, the hydrogen and oxygen are broken down. Hydrogen, being very light, would leave our atmosphere and water would slowly evaporate. This is what we think happened to Mars. Because Mars doesn't have strong magnetic field, this is how we think Mars lost its water, although it had oceans similar like Earth. So this is one reason that this magnetic field allows Earth to be habitable, to be supportive of life, because we think the easiest way to make life is having water, liquid water on the surface of a planet. But another reason is once you create life, you have to protect it from cosmic rays. Cosmic rays are again created in these supernova explosions, and they travel throughout the galaxy. They're the highest energy particles there are. And if they're able to come to the surface of a planet, they would irradiate living organisms. What that means is they would go through our body and dissociate water inside our bodies. And we know we're mostly made of water, which that means it will create genetic mutations, and the life wouldn't be able to progress as fast as possible. So our magnetic field protects us by preserving our water and protecting us from these cosmic ray particles, which have to go around, they have to follow magnetic field lines and go around our Earth. Of course, some of these particles from solar winds do come in through some regions of magnetic field, but they give us these beautiful auroras that we see. So when we then look, why is there the only place that maybe captured this aluminium-26? Why Mars and Venus didn't have that aluminium-26? We have to then look back and figure out what is the distribution of this element. Because aluminium-26 decays over 1 million years, the supernova events that we think have created our solar system would have long gone by now. The humans came on the scene. So we can't observe aluminium-26 anymore directly, but we can observe magnesium-26, which is an element in which aluminium-26 decays. And this line of magnesium is emitted in gamma ray wavelengths, which is some of the highest energies that we can observe. So we need a satellite to launch them above our atmosphere and observe this line. So what we can do now is basically try and see if we map, you see here a rough map of the galaxy in magnesium line, but we can now zoom on individual stellar-forming regions to understand, is this emission uniformly distributed, and therefore maybe all terrestrial planets in that solar system should be habitable? Or maybe somehow, for some unknown mechanism to us at the moment, this aluminium-26 is clumped up, and only certain planets get to embed it into their larger body. So these are the way that we untangle the story. We find something unique and then try to find the reason why that exists. So to me, that's a part of the science, understanding that process and behaving like a detective and trying to find the answer. So this way we know supernova remnants can create habitable worlds. They can create worlds that support life. But we also know they're highly destructive. they would, if there's any planets around these stars, they will be destroyed by this explosion. Basically, it's one of the most massive events in the universe, and they will be just engulfed, and any life will be obliterated if there is time to develop life. But they don't pose just threat for the planets around them. They also pose threat for relatively nearby objects, because they release so much energy. They release so much gamma rays that basically they could come and do the damage, even with or without magnetic field. We would not be protected if we have relatively nearby supernova remnant. So if we get irradiated, we would all turn as superheroes and like Fantastic Four, and that would be great. But in the worst case scenarios, only cockroach will survive. Cockroaches, they have bodies with the least amount of water, so they would suffer the least amount of genetic mutation, and they'll be able to go on and continue for us. Luckily, we know that there is no massive star within 75 light years, which is roughly the distance that would take to reach us for some of these emissions. So we can all rest in peace that we're not going to be irradiated and cockroaches not going to take over our world. Thank you.